Hi everyone! Today, we're going to continue learning about homogeneous linear differential equations with constant coefficients. This time, we'll focus on initial value problems and boundary value problems. These are ways we apply that we've learned to solve problems where certain conditions are given at specific points. A homogeneous linear differential equation with constant coefficients is a differential equation where all terms involve the function or its derivatives. So the coefficients are constants and the equation is equal to 0. The constant coefficients are the numbers that multiply the derivative of y. These coefficients do not depend on the independent variable. How do we solve homogeneous linear equations with constant coefficients? So the general form is a sub n times y to the power of n plus a sub n minus 1 times y to the power of n minus 1 and so on up to a sub 1 times y prime plus a sub 0 times y equals 0. The coefficients a sub n minus 1, and so on, up to a of 0 are constants. These are the three cases and their solution form on how to solve characteristic equation for roots.
Good day, everyone. Today, we'll be discussing initial and boundary value problems, an important topic in differential equations, particularly in the study of homogeneous linear equations with constant coefficients. Initial value problem. Type of problem involving the use of initial condition. A known constant requires the use of initial condition. The problem of finding a function y of x when we know its derivative and its value y sub 0 at a particular point x sub 0 is called an initial value problem. This problem can be solved into two steps. Number 1, solve for a general solution. Number 2, using the initial data, plug it into the general solution, and solve for C. Solving a second-order homogeneous differential equation initial value problem with distinct real roots. For example, find a solution to the differential equation if y of 0 is equal to 5 and y prime 0 is equal to 27. 3 second derivative plus 18y prime plus 15y is equal to 0. Solution: 3 second derivative plus 18y prime plus 15y is equal to 0. 3r squared plus 18r plus 15 is equal to 0. Factor out 3r plus 3, r plus 5 is equal to 0. So, to find r1, 3r1 plus 3 is equal to 0. Transpose 3r sub 1 is equal to negative 3 divided by 3 r1 is equal to negative 1. So to find the r2, r sub 2 plus 5 is equal to 0. r sub 2 is equal to negative 5. We already find the r sub 1 and r sub 2, which is equal to negative 1 and negative 5. We're gonna use the general solution, which is y sub x is equal to c sub 1 e raised to negative x plus c sub 2 e raised to negative 5x. If y of 0 is equal to 5, we're gonna substitute it. 5 is equal to c sub 1 e raised to negative 0 plus c sub 2 e raised to negative 5 times 0. 5 is equal to c sub 1 times 1 plus c sub 2 times 1. 5 is equal to c sub 1 plus c sub 2. So, c sub 1 is equal to 5 minus c sub 2. If y prime 0 is equal to 27, y of x is equal to c sub 1 e raised to x plus c sub 2 e raised to negative 5x. Y prime of x is equal to negative c sub 1 e raised to negative x minus 5 c sub 2 e raised to negative 5 times x. 27 is equal to negative c sub 1 e raised to negative 0 minus 5 c sub 2 e raised to negative 5 times 0. 27 is equal to negative c sub 1 minus 5 c sub 2. We can substitute c sub 1 is equal to 5 minus c sub 2. 27 is equal to negative 5 minus c sub 2 minus 5 c sub 2. 27 is equal to negative 5 plus c sub 2 minus 5 c sub 2. 32 is equal to negative 4 c sub 2. So divided by negative 4 to cancel out, c sub 2 is equal to negative 8. Plugging c sub 2 is equal to negative 8 into c sub 1 is equal to negative 5 minus c sub 2. To solve for c sub 1, we get c sub 1 is equal to 5 minus negative 8. C sub 1 is equal to 13. Now, we can take c sub 1 is equal to 13 and c sub 2 is equal to negative 8 and plug them into the general solution. Y of x is equal to c sub 1 e raised to negative x plus c sub 2 e raised to negative 5x. Y of x is equal to 13e raised to negative x plus negative 8e raised to negative 5x. So the final answer is y of x is equal to 13e raised to negative x minus 8e raised to negative 5x. Thank you.
Boundary value problem. For differential equations of second order and higher, we can also determine a particular solution by specifying what are called boundary conditions. A system of ordinary differential equations with solution and derivative values specified at more than one point. Most commonly, the solution and derivatives are specified at just 2 points, the boundaries defining a two-point boundary value problem. Example, condition if y of 0 is equals to 1 and y prime of 2 is equals to 5. Example for solving the BVP. Find the solution to the differential equation if y sub 0 is equals to 0 and y sub pi is equals to 2. The second derivative of y minus 3y prime plus 2y is equals to 0. The solution is copy the equation and ito y is magiging r. So r squared minus 3r plus 2 is equals to 0. R minus 1 times r minus 2 is equals to 0. The value of r sub 1 is equals to 1 and r sub 2 is equals to 2. The general equation, to solve the general equation is y sub x equals to c1e raised to r1x plus c2e raised to r2x. Y of x equals to c1e raised to x plus c2e raised to 2x. If y sub 0 is equals to 0, y sub x is equals to c1e raised to x plus c2e raised to 2x. The y sub 0 is equals to c1e raised to 0 plus c2e raised to 0. So 0 is equals to c1 plus c2. And c2 is equals to negative c1. If y sub pi is equals to 2, y sub x is equals to c1e raised to x plus c2e raised to 2x. So 2 is equals to c1e raised to x plus c2e raised to 2 pi. To substitute, c2 is equals to negative c1, 2 is equals to c1e raised to pi plus c2e raised to 2 pi. 2 is equals to c1e raised to pi minus c1e raised to 2 pi. 2 is equals to c1 times e raised to pi minus e raised to 2 pi. So the answer is c1 equals to 2 over e raised to pi minus e raised to 2 pi.
Since we already found the value of c sub 1, which is 2 over e to the power of pi minus e to the power of 2 pi, now we are going to solve for the c sub 2. So using the equation 1, which is c sub 2 equals to negative c sub 1, we are now going to substitute the value of c sub 1. So c sub 2 is equals to negative 2 over e to the power of pi minus e to the power of 2 pi. So we just change the sign of c sub 1 to find the c sub 2. Now that we already found our two constant, we are now going to substitute the constant in the general form. So remember, we have the general form of the solution, which is y sub x equals to c sub 1 times e to the power of x plus c sub 2 times e to the power of 2x. So substitute the two constants. So the result is y sub x is equals to 2 over e to the power of pi minus e to the power of 2 pi times e to the power of x minus 2 over e to the power of pi minus e to the power of 2 pi times e to the power of 2x. So we can still factor our general equation. So factor out 2 over e to the power of pi minus e to the power of 2 pi. So the final answer is y sub x is equals to 2 over e to the power of pi minus e to the power of 2 pi times e to the power of x minus e to the power of 2x. As you observed in our examples, you can spot the difference between initial and boundary value problem, where in IVP involves finding a solution to a differential equation that satisfies specified conditions at a single point, typically the starting point of the domain. Just like for example, an aton example kanina, an IVP where an aton x is at a single point which is 0. The BVP or the boundary value problem, it seeks a solution to a differential equation that satisfies condition at two or more distinct points, often at the boundaries of the domain. Just like for example, naton example kanina, han BVP, where there is two distinct points which is the 0 and pi. Thank you for listening to our discussion. We hope you learned something meaningful about solving homogeneous linear equation with constant coefficients.